Hello everyone and welcome. I'm Rishikesh Paudel. Today, I along with my teammates are excited to introduce our case study on cyber physical system for the car manufacturing industry. Our case study on object-oriented analysis and design has three main objectives as shown below. To enhance automation on the production floor of car manufacturing industry, to optimize production efficiency by streamlining processes, to enable predictive maintenance so we can detect and fix issues before they cause downtime. To achieve these objectives, we have outlined several key tasks. First, we connect physical devices like robotic arms and sensors with our cyber systems to ensure smooth data flow and process synchronization. Second, we make sure that the communication between these devices happens with very low latency, which is essential for real-time monitoring and adjustments. Third, we apply machine learning techniques to predict equipment failures before they occur, reducing downtime. And lastly, we implement energy-efficient solutions to monitor and cut down on factory energy uses. Our system is built around a set of functional requirements that ensure it does what it needs to do. It must seamlessly integrate physical and cyber systems. It should offer real-time monitoring and control. Low latency communication is essential. It must support predictive maintenance. It needs to be energy efficient. A user-friendly interface is a must. It should integrate and store data effectively. Automation and process optimizations are key. The system must be scalable for future growth, and it should include fault detection and recovery mechanisms. Alongside these core functionalities, we have non-functional requirements to ensure quality. High performance, strong reliability, robust security, scalability in design, energy efficient throughput, excellent usability, accessibility for all users, privacy protection, interoperability with other systems, easy maintainability, low latency even under heavy loads, fault tolerance for continuous operation, compliance with standards, and cost effectiveness to manage expenses. Finally, we look at our use case diagrams. Here we identify the key users of our system. Operators who run the day-to-day processes, system administrators who maintain the system, production managers who oversee operations, maintenance engineers who handle repairs, quality control specialists ensuring standards are met, and last but not the least, energy management personnel who focus on efficiency. This slide visually represents how these actors interact our system, giving us clear picture of each role and its responsibilities. Now, to tell about the class diagram, I'd like to call my friend Nabin.
So this class diagram represents the cyber physical system in a car manufacturing process. It consists of multiple components working together to ensure smooth operation, automation, and security. So firstly, we have the user interface. The user interface allows human operators to interact with the system. It has attributes such as user role and functions such as display data, resolve input, trigger alert. So it interacts directly with the controller, enabling users to monitor and control the system. Then we have the sensor. The sensor collects real-time data such as temperature, pressure, or position class with attributes like type, input, type, unit, and value. So it sends this data to the controller, which processes it and for decision making and sends it to the controller. Then we have the controller. The controller is the brain of the system. It processes sensor data, generates logs, and sends commands to actuators. It acts as a bridge between different components, ensuring efficient control over the manufacturing process. Then we have the processing unit. Processing unit performs computations on incoming data. It executes algorithm and runs AI models to analyze production data. The results are stored in the database and uploaded to the cloud service. Then we have database class. The database stores processed data with attributes like storage capacity and data format. It allows retrieval of historical data, ensuring efficient access and backup mechanisms. Then we have the cloud service class. Cloud service enables remote data storage and management. It uploads process data, analyzes AI model, and synchronizes with the database, ensuring seamless integration of physical and digital components. Then we have the security module. The security module ensures secure communication by authenticating users, encrypting data, and verifying integrity. It prevents unauthorized access and works closely with the network module to protect data transmission. Then we have the network module. The network module handles communication between all components. It transfers sensor data, control signals, and cloud updates efficiently with attributes like protocol, bandwidth, and latency. And finally, we have the actuator. The actuator performs physical actions based on controller commands. It can move robotic arms, adjust machine parameters, or trigger safety mechanisms. It also has a self-check function to ensure reliability.
My name is Prafulla Raj Pokhrel and I will be further presenting on collaboration diagram. The collaboration diagram illustrates how our cyber physical system facilitates human system interaction across departments. Production goes from management to analytic platform which generates performance report for data analytics to derive optimization insights. The maintenance team receives automated alerts from the system, with IT support handling technical issues and escalating complex problems to the platform. Two cross-cutting processes are essential: continuous performance monitoring across all departments and collaborative problem solving between maintenance and IT. These two tasks are performed in a single individual stakeholder without the involvement with each other, without the collaboration with each other. The next diagram we are going to talk about is sequence diagram. Our system integrates five key components: IoT sensors that monitor production in real time, robotic arms performing manufacturing tasks, a central analytic platform for data processing, operator interface for human supervision, and maintenance team. The sequence diagram shows three operational scenarios. In normal operation, sensors feed data to an analytic platform which directs robotic arms while keeping operators informed. Our predictive maintenance flow use machine learning to anticipate issues before they occur, reducing downtime. In fault detection scenarios, the system quickly routes error signals to both operators and maintenance personnel with diagnostic information. These they are the activities are handled in this sequence. The which in the happen in this sequence. It is for the low optimization, communication, and energy optimization. The next topic is state diagram. The state diagram complements this by showing how our system transitions between operational states. During normal operation, the system cycles from the idle through scanning, processing, moving, and executing task states. Safety is built with dedicated states for obstacles avoidance and error handling, with any critical failures triggering an immediate shutdown. From any states, our system can transition to error handling if problem detected. We can see here in state diagram in any state without the error occurring. If any error occur, and error handling is there. If the error is very critical, then it further process directly to the shutdown. The shutdown command is received, it will go in the ideal situation. So after restart command received, it will do scanning the environment. It is scanned, processed, the movie, it will move the car will move and the obstacle will be avoidance. If it is moving, if it has reached the target, it will follow up as a task completed. If it has not reached the target, it will be further move in its own path. These diagrams together demonstrate how our cyber physical system maintains operational integrity while optimizing production efficiency. The architecture emphasizes low latency communication and energy optimization throughout, enabling real-time monitoring, predictive maintenance, and rapid fault response, all critical for maintaining production quality in automatic manufacturing. Thank you.
Hello everyone, I am excited to present to you our activity diagram and the deployment diagram for the cyber physical system in car manufacturing industry. We have developed the comprehensive framework that integrate the entire production life cycle, raw material handling, predictive maintenance, system updates, and all powered by a robust interconnected architecture. Let us walk through the production process in the system. In the activity diagram, basically represents the flows. It is the flowchart representation of all the processes that is happening in the system. It begins with the system initialization and the material validation, ensuring that only approved materials enter the approved materials enter the robotic assembly phase, and it checks and guarantees that every product meet the high quality standard, and it is done by real time IoT sensors monitoring, and the system immediately implements adjustments if the defects are detected, showcasing its ability for real-time maintenance. And following the production, we move into the predictive maintenance using the sensor using the sensor that data to anticipate and prevent equipment failures, minimizing downtimes, and and give a seamless operation throughout the process. We analyze the energy consumption and generate the performance reports, which inform the data driven system updates, ensuring continuous improvement. And the closed loop system highlights our commitment to efficiency and quality. Now, going to the deployment diagram, this shows the relationship between the hardware and the software processes that are taking place in the system. It is a powerful interconnected architecture as depicted in our deployment diagram. The core is here at the factory server, acting as the central hub. It communicates to the soft floor via IoT gateway using the lightweight protocols like MQTT and TCP/IP for sensors and actuators, and control signals are used for the robotic arms controlling. The operators interact through the workstation using the REST API and the WebSockets for real-time monitoring. Crucially, all the production data is backed up to the cloud. All the production data is backed up to the cloud and analyzed through the cloud analytics performance. This architecture enables a data-driven approach in decision making, and remote monitoring. Also, it is scalable and it ensures robust and adaptable system. Thus, by integrating this in the cyber physical system in car manufacturing, it demonstrates a holistic approach combining a well-defined production process and a robust architecture that can revolutionize the manufacturing. Thus, the system is not just about building the products; it's a smarter, more responsive, and sustainable future for manufacturing. Thank you.